Suman Bera is a postdoctoral researcher at UC Santa Cruz, working with Professor Sesharthi. He obtained his PhD in computer science from Dartmouth College when he was advised by Professor Amit Chakrabarty. He completed his master's at IIT Delhi under the supervision of Professor Amit Kumar. He also has spent a couple of years at IBM Research Lab in New Delhi and Adobe India. Suman's research is broadly on topics of foundations of data science. In particular, he's interested in large graph analysis. His work lies in the intersection of theoretical computer science and data mining, and he's also interested in algorithmic fairness. Today, we are pleased to have Suman, and he's going to tell us about his recent work on subgraph counting, which has been published in SODA and ITCS, which are both important theoretical CS venues. Please.
Thanks, Shaza. Thanks for the introduction, and thanks for inviting me to give this talk here. I'm very happy to be here and to share with you my two of my recent results. So feel free to ask me questions during the talk. You can just unmute yourself and ask the question. So this talk is going to be based on two papers. Both of these papers are on the topic of subgraph counting and some variants of it. So let me start with defining the subgraph counting problem. So let's say we have a small pattern graph H. Now H is not an input, but it's part of the problem description. The input to this problem is a large input graph G, and the goal is to count the number of copies of H in G. So we denote this problem as sub H of G. And we make this distinction here. We are not interested in counting just induced copies. So by that, I mean the following. Let's say H is a 4 cycle, and these orange edges on the right, they form a 4 cycle, but they do not form a 4 induced cycle because of the blue diagonal edge that's present there. So that's okay with us. So we are interested in counting the copies of H in G, but these copies may or may not be induced copies. And throughout this talk, whenever I talk about H, you should really think of it as like a small constant size pattern graph that we are trying to count in a really large graph. So we think of H as a constant size graph. So this subgraph counting problem has been studied by various communities because it has a diverse set of applications. For example, it has application in social network analysis, in understanding community behaviors. Triangles and cliques in particular has been studied intensively in order to define various of these parameters for social network analysis. It has also found some interesting application in spam detection, in graph mining to find interesting topics on the web, and also in biological networks where motifs or interesting subgraphs in protein-protein interaction networks, for example, reveal about the structure of the network. And also from a theoretical point of view, this problem has been studied quite intensively. So for various of these problems, for various of specific subgraphs, there are exact algorithms known, there are approximate algorithms known. Also, it has been studied whether there is a gap between the deterministic and randomized complexity of solving this problem. And this problem has also been studied in various big data models, such as the MapReduce model or streaming model, etc. So if we go over this application, one thing that keeps recurring is that the graphs in which we are interested in counting these subgraphs are really large networks. So for some examples, if we look at the social network graph, it can have few billion edges to few 100 billion edges. If you look at the web graphs, again, it's a very large graph and possibly having a few 100 million or few 100 billion edges. So any algorithm that solves this subgraph counting problem really needs to be a linear time algorithm. If you are going beyond linear time, that becomes really impractical. So our focus is on understanding when linear time algorithms are possible for various subgraphs. One other feature of these large networks is that they are sparse. So we need to have some kind of parameter to measure sparsity. And in this work, we focus on this parameter called degeneracy. So I'll not define degeneracy here exactly, I'll do it later in the talk. But intuitively, you can think of degeneracy as a measure of maximum average degree of any subgraph of G. So you look at any subgraph of G and you look at the average degree of that subgraph, and then you take the maximum over all possible subgraphs of G, and degeneracy captures that quantity. So intuitively, if a graph has low degeneracy, you should think of it as like all subgraphs are sparse. Now, degeneracy is also known as the K-code number or the coloring number. And if you are familiar with arboricity, then degeneracy is closely related to the concept of arboricity as well. They are off by a factor of 2. And the reason for considering degeneracy as a sparsity parameter is that there has been a lot of studies in understanding degeneracy of a social network or a large network, and it has been shown that the degeneracy of these graphs are often quite small. So for example, if you take the example of a Facebook graph, which can have a maximum degree quite large. If a person is really popular, it may have many followers. But the degeneracy of these graphs are often in hundreds. It's less than 1,000. So the main theme of our work is to answer the following questions. What kind of subgraphs are linear time countable in large sparse network? So we are interested in linear time countable because these graphs are really large. We don't want to go beyond linear time algorithms. And we are interested in sparse networks, not in dense networks. And so when we're talking about subgraph counting problem here, we are interested in finding the exact count, not an approximate count. So the first problem that we consider is the k-vertex subgraph count problem. We denote this as subcount k. Again, k is not an input parameter, but it's part of the problem description. So the subcount k asks for the count of all connected k-vertex subgraphs in the input graph. So for example, if k is 3, then we are asking for the count of the triangles or counts of the count of the triangle or count of the 2 paths in the input graph. If k is 4, then we are asking for the count of all 4 vertex connected subgraphs, which includes the 4 cycle, the 3 path, or the 4 click, and so on. And there is another example for k equal to 5. So the problem that we have, or the problem that we try to answer is the following. For what values of k, subgraph count k is solvable in linear time in bounded degeneracy graph families. Now, when I say bounded degeneracy graph families, you should think of the degeneracy really as a constant. So we discover a surprising chasm, and this is the result from the ITCS 20 paper. So we prove that if k is at most 5, then the subgraph count k is solvable in linear time, which is to say that you can count all connected 5 vertex subgraph in linear time, 5 or less vertex subgraph. However, if k is bigger than 6, then the problem is not linear time countable anymore, assuming that triangle counting or triangle detection problem is not solvable in linear time. Now, this triangle counting conjecture is a very popular conjecture. I'll talk in more details about this conjecture later. But this is kind of a believable conjecture that if you want to detect whether a graph has a triangle or not, you really need to do more work than just parsing the graph. So I'll give more evidence of why this is a very reasonable looking conjecture. So this is our first result. So a little bit in more details. We already knew that subgraph count 3 was solvable in linear time in order m alpha time, where alpha is the degeneracy of the graph, which we are treating as constant in this work. And this is due to earlier work by Chiba and Nishijeki, which kind of started this, this particular area of subgraph counting in sparse networks. By a series of work, it was also been established that subgraph count 4 is also solvable in linear time. So our main algorithmic contribution was to design an algorithm that can solve the subgraph count 5 problem in linear time. So basically, we design an algorithm that can count any 5 vertex subgraph in linear time. And we also show that for k greater than or equal to 6, there always exists some k vertex subgraph such that you can't count the copies or number of copies of this subgraph in linear time. And this is a conditional hardness, assuming that triangle counting is hard or triangle counting is not in linear time. There is always some subgraph for k greater than or equal to 6 for which you can't solve this problem. Now, the particular hard instance of the graph that we consider is k cycles. For almost all values of k, we show that it's the k cycle which is the hard subgraph that we cannot count in linear time. Now, after this work, we ask the following question: is it possible to get a tighter characterization on what kind of subgraph exactly we cannot count in linear time? So for example, in the work of Chiba and Nishijeki, it was implicit that if you are trying to count any constant size click, you can do it in linear time. So it does not matter if this click has size 6 or 7 or 8. If the click has constant size, you can count it in linear time. And our algorithm also suggests that if the graph looks like click minus a few edges, then also you can count it in linear time. So we basically want to characterize precisely the pattern graphs H for which this problem is not solvable in linear time, or otherwise, in the other way, like for what kind of pattern graphs H we can solve the sub H of G problem in linear time. So this is the focus of our next question. However, while trying to solve this problem, we realize that the characterization becomes much simpler if we look at a variant of the subgraph count problem, and that is the graph homomorphism counting problem. So in the next few slides, I'll talk about the homomorphism counting problem, and then we'll come back to this characterization question. So homomorphism of H to G is a mapping of the vertices of H to the vertices of G that preserves the edges of H. So for example, let's say H is a 4 cycle and G is something like this, the green graph. So let's say I consider the following mapping. 1 goes to A, 2 goes to B, 3 goes to A, and 4 goes to B. So the condition for homomorphism says that whenever there is an edge in H, the corresponding edge should be there in G as well. So for example, if you look at the word edge 1 and 2, the corresponding edge A and B is present. Similarly, if you look at the edge 2 and 3, it again maps to the same edge A and B. The same is true for all the 4 edges in the cycle. So we collect this pattern, the kind of pattern that we get in G, and we call them the quotient graph. So quotient graph of this cycle includes an edge. Now I'm not going to define what quotient graphs are formally, but think of it like whenever we are looking at a homomorphism of this graph H, what kind of pattern we discover in G. So in this particular example, we discovered that this is an edge. So let's take another example. Let's say in this case, 1 is mapped to A, 2 is mapped to C, 3 is again mapped to A, and 4 is mapped to B. So this is again a valid homomorphism because all of these edges are present. 1 and 2 gets mapped to A and C, 2 and 3 gets mapped to again A and C, and so on. So in this case, the pattern that we discover in G is 2 path. So we will collect this in the quotient graph for H. Let's look at one more example of a homomorphism. Let's say 1 is mapped to A, 2 is mapped to B, 3 is mapped to C, and 4 is mapped to D. So in this case, the pattern is basically 4 cycle in G as well. So this is an injective mapping. It's sometimes also called embeddings. So it corresponds to subgraph counting almost, because you also have to consider the automorphisms, like the vertex 1 might get mapped to A, or it can get mapped to B also, and you can still get a valid homomorphism. So the quotient graph that we get in this case is the 4 cycle. So the homomorphism counting problem asks for the number of such mappings from H to G. And we denote this problem as hom H of G. And when the injective if the homomorphism is injective homomorphism, then we sometimes call them embeddings. So embeddings are almost like subgraph copies, but the count of embeddings are slightly different from the count of homomorphism because you also have to consider the automorphisms. So the next question that we ask is the following. So the question is, can we characterize the pattern graphs H for which the homomorphism counting problem is solvable in linear time. And we'll see later how this problem is related to the subgraph counting problem. So in order to answer this question, we define this parameter of H, which we call the LICL, which stands for length of the longest induced cycle in H. So for example, let's say H is a graph which looks something like this. Then the length of the longest induced cycle in this graph is 3. If H looks something like this, then the length of the longest induced cycle is 6. And here is another example where the length of the longest induced cycle is 4. Now note that it's the length of the longest induced cycle. So for example, in the first graph and in the last graph, the length of the longest cycle could be large if you're not looking at the induced cycles. But this parameter is actually for induced cycle. So our results are as follows. We show that for a pattern graph H, if the length of the longest induced cycle in H is at most 5, then we can solve the homomorphism counting problem in linear time. And if the length of the longest induced cycle is more than 5, if it is 6 or larger, then there is no linear time algorithm for solving the homomorphism counting problem, assuming this triangle counting conjecture. So again, we discovered this chasm at 6, which basically separates what kind of subgraphs or what kind of pattern graphs for which we can count the homomorphism in linear time. So this is the main result of our SOTA paper. And I should also mention that independently, Gish-Bolliner, Levanzov, and Shapira, they also discovered this same result. Now, this homomorphism counting problem has a consequence for the subgraph counting problem as well. So this basically gives the following theorem. Subgraph count is linear time solvable if and only if every quotient graph of the pattern graph H has length of the longest induced cycle at most 5. Now, I'll not go too much into details why this is a consequence of the previous result, but it's known that the subgraph count can be written as a linear combination of the homomorphism counts of all subgraphs that are in the quotient graph of that subgraph. So for example, we saw some example of quotient graphs for 4 cycles. And for triangles, the quotient graph is just triangle itself. You spend some time, you will see that. So there is this relationship that if I'm trying to get the subgraph count of a graph, then it can be expressed as some linear combination of homomorphism counts of all the pattern graphs that are in the quotient graph of this subgraph. Now, this leads to some interesting results. For example, if I'm looking at the 7th path, the homomorphism counting result says that the 7th path, you can count the homomorphism of 7th path in a large bounded degeneracy graph in linear time because it doesn't have any cycle. But 7th path will have the 6th cycle in its quotient graph because you can connect the 2 endpoint of this 7th path in a mapping and you will get this 6th cycle. So 6th cycle will be a quotient graph for the 7th path. So if I'm trying to count the subgraph count of the 7th path in a graph, I cannot do that because it contains this 6th cycle in its quotient graph, and counting homomorphism for 6th cycle is hard. So we get this separate result for subgraph counting and homomorphism counting. So this is kind of all the results that we have. So now I'll go into the details of some of these results. If you have any questions about the main results of our work, this would be a good time to ask. Cyrus, I think you have a question. Yeah.
Yes, I believe you said something a while ago about cliques being easily counted.
Right.
So why does the 7 clique not also have a quotient graph that is a 6th cycle? Or is that a valid question?
No, that's a valid question. So the reason is the following. So when we are looking at the quotient graph, effectively what we are doing is that we are looking at an independent set of that graph and collapsing that independent set into a single vertex. So the clique does not have an independent set. Its independent set is basically empty. So that's why clique does not have 6th cycle in its quotient graph. I hope that makes sense.
Yes, thank you.
Okay, so let me move on to the first technical part of the work. Go over some of these lower bound results. So our lower bounds are conditional lower bounds that are based on triangle detection conjecture. So this conjecture was first formalized by Aboud and Williams in their Fox 24 paper, and they proved a lot of lower bounds for well-known graph problems in the dynamic setting using this conjecture. The conjecture says that triangle detection requires superlinear time in expectation. So the best algorithm for triangle detection is due to Allen, Euster, and Zwick. And the complexity of this algorithm is n to the power omega, m to the power 2 omega by omega plus 1, where omega is the matrix multiplication exponent. And these techniques are also based on fast matrix multiplication. So it is believed that the best algorithm for triangle detection requires m to the power 4/3 time, corresponding to omega equal to 2. So it is reasonable to believe that there is no linear time algorithm for triangle detection or triangle counting. And if there was an algorithm that can solve this problem in linear time, that would be a very surprising and big breakthrough results in graph theory. And note that the lower bound is stronger than the popular lower bound that is assumed is stronger than the lower bound that we are assuming. We're just assuming that it's not doable in linear time. Okay, so let me just recap the two main lower bound results that we have. Assume the triangle counting or triangle detection conjecture. The first result is to show that for every k greater than 6, there exists a k vertex subgraph H such that its subgraph count is not possible to compute in linear time. And the hard subgraph instance is going to be the cycles. And the second result is that if the length of the longest induced cycle in H is at least 6, then the homomorphism count is not linear time solvable. So I'll first talk about the first result. So due to some technicalities, we will prove the hardness for cycles, but not when k is equal to 8. For k equal to 8, we consider a slightly different graph, but this is due to the technicalities of our proof construction. We still believe that counting 8 cycle is still hard, just that the proof technique that we have is not going to give that lower bound. Okay, so the idea is to reduce the triangle counting problem in general graph to the cycle counting problem in a bounded degeneracy graph. So I'll first do this proof for the 6 cycle. I'll show that subgraph count for 6 cycle is a hard problem, hard in the sense that it's not linear time solvable. So we have a triangle counting problem in a general graph, and we want to reduce this to the 6 cycle counting problem in a bounded degeneracy graph. So the reduction works as follows. For each edge in the original input graph, we split it into a 2-path, and we get a new graph. So for example, if there was a triangle in the original graph, this triangle will now become a 6 cycle. But the original graph did not have bounded degeneracy. So the original graph is an arbitrary general graph. But this process ensures that the new graph that we obtain by splitting every edge into a 2-path, this new graph will have degeneracy exactly 2. It's a bounded degeneracy graph. Now, since I did not define degeneracy exactly, I'll not argue why this graph has degeneracy of 2. But, excuse me, intuitively, you can see that in this new graph, we are introducing a lot of new vertices. So if the original graph has n vertex and m edges, the new graph that we got will actually have order m vertices and order m edges. So this new graph is quite sparse. So, and we can argue precisely that this new graph has degeneracy exactly 2. So now the next argument is that the number of 6 cycle in this new graph that we constructed is exactly equal to the number of triangles in the original graph. So you will have a 6 cycle in this new graph if and only if you have a triangle in the original graph and there is actually a 1-to-1 mapping between the triangles in the original graph to the 6 cycles in this new graph. So this basically shows that if I can solve the 6-cycle counting problem in a bounded degeneracy graph in linear time, I can use that to solve the general triangle counting problem in an arbitrary graph. Now, this idea can be generalized. Let me show you another example of how to prove a lower bound for 7-cycle counting. Now, in this case, what we do is that we split every edge into 2 parallel paths, one having 2 edges and another one having 3 edges. So each edge converts into a pentagon. So now let's look at a triangle in the original graph. Now this triangle will look something like this. So for every edge, we replace it with 2 parallel paths, one of length 2 and one of length 3. Now this structure has exactly 3 7-cycles. You can consider one green 3-length path and 2 yellow and blue 2-length paths, and that will give you a 7-cycle. Similarly, you can consider the yellow 3-length path and blue and green 2-length path, and so on. Now again, this resulting graph is quite sparse because we are creating 3 new vertices for every edge in the original graph. So this new graph again has order m many vertices and order m many edges, and we can argue that this graph has degeneracy exactly 2. And the number of 7 cycles in this new graph will be exactly 3 times the number of triangles in the original graph. So every triangle will basically result in 3 7 cycles in this new graph. And also, if the original graph was triangle free, then there won't be any 7 cycles in this graph, and we can formally argue this. Now, you can also see why the 8 cycle does not work, because it's possible that if we have the same construction for 8 cycle, let's say the original graph did not have any triangle, but it had some 4 cycles. Now, these 4 cycles will lead to a lot of 8 cycles in the constructed graph, although the original graph was triangle free. So by looking at the 8 cycle count in this newly constructed graph, we can't discover how many triangles were there in the original graph. Now this just happens for 8. For all other values, this checks out. So the general framework is as follows. So let's say k is 3l plus I, where I is some integer between 0 to 2. So if I is 0, we split an edge into an L path. And if I is non-zero, then we split it into 2 parallel paths, one having length L, one having length L plus 1. And we can show that this newly constructed graph will have bounded degeneracy, and it still has order m edges. And the number of ck in this newly constructed graph is a function of the number of triangles in the original graph. So in other words, each of these ck can be uniquely mapped to a triangle in the original graph. So that is basically the idea behind the lower bound proof in the first one. Okay, so now let's move on to the next lower bound, which says that if the length of the longest induced cycle is more than 6, then the homomorphism counting problem is hard, assuming the triangle direction conjecture. Now the overall strategy still remains the same, but the construction is now significantly more complicated. Because if you think about it, what we are trying to do is that we are trying to get the triangle count in the original graph from the homomorphism count in the newly constructed graph that we get. But as we saw in the previous, in the slides where we are discussing the homomorphism counts, a homomorphism of, for example, a 4 cycle can involve a 4 cycle or a 2 path or even a single edge. So homomorphism has a lot of graphs in its quotient graph, and it's basically counting all of them. So if I'm trying to get the triangle count by just looking at the homomorphism count, it seems a very difficult task, because homomorphism involves this lot of different type of patterns. Now, in order to overcome this problem, we defined a partition homomorphism problem. So the partition homomorphism problem is effectively trying to simulate one-to-one mapping in the homomorphism, or injective homomorphism. So the problem is defined as follows. let's say the vertex set of the original graph is partitioned into k non-empty subsets. So for example, let's take this example again. Let's say this graph G, its vertices has 4 colors, because H in this case is 4 cycles. So we partition the vertex set into 4 groups. Now, partition homomorphism or P homomorphism is a homomorphism in which each of these colors are mapped by some vertices, some vertex of the graph H. So for example, if my homomorphism looks like this is not a partition homomorphism, because not all colors in G gets a mapping from H. For example, in this case, the red vertices and the yellow vertices, they don't have any image in H by this mapping. So this is not a partition homomorphism. On the other hand, if I look at a homomorphism that looks something like this, then this is a valid partition homomorphism, because it's one-to-one and each of these mapping is to a different colored vertex. So in some sense, by defining this partition homomorphism problem, we are trying to simulate the subgraph count problem with some caveat. I mean, you still have to consider some automorphisms. But otherwise, we are trying to get rid of smaller size subgraph that can result in from a homomorphism. So after this definition, our strategy for the reduction is as follows. It's a Turing reduction. So we start with this input graph G, in which we are trying to count the number of triangle. We again do some edge splitting to construct a sparse graph G prime. So the ideal goal would have been to count the number of homomorphisms of H in G prime and then derive the number of triangles from that count. But that seems like a difficult task. So instead, we define a careful partition on the vertex set of G prime. So we constructed this graph G prime and we define a partition on this graph G prime. And we prove that triangle count in G follows from the P homomorphism count of H in G prime for an appropriately defined partition of this vertex set. So this is more believable because each of these homomorphisms are now kind of looking like a subgraph because it's a partition homomorphism. And we can derive the triangle count we can possibly derive the triangle count by looking at this P homomorphism counts. I'm not going to go into the technical details of how these partitions, etc., are defined. But still there is a problem. Like the problem is, how do I compute the partition homomorphism count? Because we have an algorithm, like we assume that we have an algorithm for solving the homomorphism count. But here we are assuming that if we knew the partition homomorphism count, then we can get the triangle counts. Now, we prove that if there is an algorithm for counting the homomorphisms of H in a bounded degeneracy graph, then we can use that algorithm to compute the partition homomorphism problem or to compute the partition homomorphism counts for any partition into k groups of the vertex set of the input graph. So this is this lemma kind of follows the inclusion exclusion argument. So combining these two lemmas basically gives us the hardness result. So we had this input graph G in which we wanted to count the number of triangles. We converted it into a sparse graph and defined some kind of partition on this sparse graph. And then we computed the partition homomorphism count for this subgraph H into this sparse graph. This is possible due to the second lemma. And once we have this count, we use that count to derive the number of triangles in the original graph. So this basically shows that if you can solve the homomorphism counting problem, then you can solve the triangle counting problem. So this is kind of the flavor of the lower bound. Not going to the details of it, but yeah, this is the high level idea of how we prove this lower bound for the homomorphism counting problem. So I'll now move into the algorithmic part. Any question on the lower bound results, if you have? Okay, so I'll now move on to the algorithmic results that we have. So we have mainly two results. The first one is that we design an algorithm that solves this subcount 5 problem in linear time. So basically, we design an algorithm to count all 5 vertex subgraph in linear time in bounded degeneracy graphs. And the second one is that if the length of the longest induced cycle in a graph is at most 5, then we show that its homomorphism counts we can derive in linear time. Now, in order to discuss this upper bound results, we need to understand the concept of degeneracy in a bit more details. So before defining degeneracy, let me define a vertex ordering of a graph. So vertex ordering is a central idea in subgraph counting algorithm, both in the applied domain as well as in the theoretical domain. So ordering of the vertices is basically an ordering of the vertices. You define some ordering of the vertices, but any vertex ordering helps us in constructing a directed acyclic graph from the input graph. So let's say my input graph is undirected and I have a vertex ordering of the input graph. Now using that vertex ordering, I can convert my undirected input graph into a directed input graph. The way to do this would be the following. Let's say there is an edge between U and V, and U appears before V in this vertex ordering. So then I orient this edge from U to V. And it's not difficult to see that this orientation is going to be directed acyclic graph. This orientation will not result in any directed cycles. Now, degeneracy can be defined as follows. There are multiple ways of defining degeneracy. This is just one characterization of degeneracy. So degeneracy is smallest k such that there exists a vertex ordering such that when you convert the input graph into a directed acyclic graph using this vertex ordering, the out degree of every vertex is bounded by k. So degeneracy is the smallest k such that there exists an ordering in which all the vertex has out degree at most k. And the good thing about this ordering is that it is very easy to get. So this is due to a result by Matula Bake from early 80s. So the algorithm is very simple. You keep removing the lowest degree vertex in the graph. And the ordering is basically the time at which you have removed the lowest degree vertex. So you get an ordering by removing the lowest degree vertex from the graph, and then you convert your input graph into a directed acyclic graph. Now your directed acyclic graph has maximum out degree of k, where k is the degeneracy of the graph, or alpha. Alpha is the degeneracy of the graph. Okay, so this is about degeneracy. The thing to remember here is that a bounded degeneracy graph will lead to a directed acyclic graph that has bounded out degree. That's basically where this degeneracy is used in these subgraph counting problems. So the basic strategy for solving this subgraph counting problem is as follows. So the first step is to construct this degeneracy ordered directed acyclic graph from the given input graph. And as we saw in the last slide, this can be done in linear time. You just keep removing the lowest degree vertex, you get a degree ordering, and you orient all the edges according to this ordering. Now, once you have converted your input graph into this directed acyclic graph, you consider all acyclic orientation of the pattern graph that you are trying to count. So you consider H arrow for all, so you consider all acyclic orientation H arrow for the pattern graph H. And now you count the copies of H arrow in this G arrow, which is the directed acyclic graph corresponding to G, and you add them up. Now the question is, why counting H arrow in G arrow is easier than counting H in G? So here this bounded out degree property comes into play. So let me give you an example. Let's say we are trying to count the number of triangles. We have converted our input graph into a directed graph, and we go over each of these edges. Let's say we are looking at one edge, UV. It's directed from U to V. Now we look at all the out neighbors of U. And by the degeneracy ordering property, there can be only alpha many out neighbors because the out degree is bounded in this directed graph. So we look at all the out neighbors of U and we see if it forms a triangle or not. So overall, this gives a order M alpha algorithm for counting triangles in a bounded degeneracy graph. So the original graph may have very high degree, but once we have converted this into a directed graph using the degeneracy, the out degree gets bounded. So now we can just go over all the edges and only look at out neighbors of the lower degree endpoint and see whether the triangle gets completed or not. So this was in fact the algorithm that Chiba and Nishizaki designed for the triangle counting problem. And in this work, we basically generalize this idea and design an algorithm for any 5-vertex subgraph that has a running time of order M alpha cube, where alpha is the degeneracy of the graph. But instead of going into the details of how we solve this problem, because I feel that this algorithm that we had was kind of ad hoc, but I'll rather focus on the second part of our upper bound, which has a more systematic way of solving this problem. So we are going to show that if a graph has induced cycle of less than 5, then we can count its homomorphism in linear time, and also it has some implication for subgraph counts as well. So this is a result due to Bresson in 2019, where he introduced this notion of DAG tree decomposition for counting subgraph, for solving the subgraph counting and homomorphism counting problem using dynamic programming. It's a very general framework. It works for any arbitrary subgraphs age. The runtime, of course, depends on the structure of age and this DAG tree decomposition. But it's a very neat result for solving this kind of problems. So intuitively, the idea is that you have this orientation of age, which you are trying to count in a directed graph G. That part still remains the same. You still convert your input graph into a directed acyclic graph, and you're still trying to count H arrow in this directed acyclic input graph. So now you decompose H into a tree such that you can run dynamic programming and in a bottom-up manner on this tree. So let me give you a bit details of what this directed tree decomposition looks like. So it has 3 properties. So first of all, we have to identify the source vertices of this pattern graph. So let's say my pattern graph looks something like this, and it has 3 source vertices highlighted by these red vertices, S1, S2, S3. So I collect these source vertices, and the tree decomposition that we are going to do, it's going to be only on the source vertices. We are going to ignore the other vertices for the tree decomposition. For every source vertex, we find what are the vertices that are reachable from this source vertex. So for example, from S1, we can reach T3, we can reach T2, we can reach T1. From S2, we can reach T2 and T1, and from S3, we can reach T3 and T2. Now, this DAG tree decomposition will take as input this acyclic graph H arrow and output a tree where each node is going to be a subset of the source vertices. That's the first property. Each node of this tree is going to be a subset of the source vertices. The second property is that the union of the node needs to cover all the source vertices. The third property is the most interesting one, which says that in the tree, if you have 3 nodes, such that B lies on the path between B1 and B2. And then if you look at the vertices that are reachable from both B1 and B2, then those vertices should be reachable from B as well. Let's take an example. Let's consider some DAG tree decompositions that are valid DAG tree decompositions for this graph H arrow. So this is one trivial decomposition. I can put all the source vertex in a single node, and this is a valid DAG tree decomposition. Instead, what I can do, I can create one node with S2 and S3, another node with S1, connect them. This is again a valid DAG tree decomposition. We don't care about the third property here because it has only 2 nodes. The first 2 properties are trivially satisfied. We are good. We can have another separate one, which looks almost similar. Now we consider another DAG tree decomposition where each node has only one source vertex. So here, yet the first 2 properties of the DAG tree decompositions are true. Now let's look at the third property. The third property says that if a node is on the path between the other 2 nodes, so in this case, S1 is on the path between S2 and S3. So then we look at the intersection of S2 and S3, the vertices that are reachable from both S2 and S3. So this is T2 in this case. So T2 is reachable from both S2 and S3. The requirement is that T2 must be reachable from S1 as well, which is the case here. So this is a valid directory decomposition for H arrow. Now let's take another example. Let's say this time S2 is on the root. But this time we see that S1 and S3 both reaches T3. But S2 cannot reach T3. So this violates the third property of the directory decomposition. So it's not a valid directory decomposition. Similarly, if we consider another one where S3 is at the root node, we see that both S1 and S2, they can reach T1, but S3 cannot reach T1. So again, this is not a valid directory decomposition. Now we have these various directory decompositions, which is the best one. So for that, we define the notion of width. So width is basically the size, maximum size of any node in that tree. So in this case, the width is 3. In this case, the width is 2 for the next two trees. And this one has width of 1. So we define the directory width of a directory decomposition to be the maximum over all the nodes, the size of that node. So this is the directory decomposition. This is just taking all this definition in one place. So the directory width of a directory decomposition is, we basically look at all possible directory decompositions and look at the one which has the minimum width. Now, why this directory decomposition is interesting? So Brayson proved the following theorem. He showed that the homomorphism problem can be solved in linear time if the corresponding subgraph H has a directory width of exactly 1. And this was a very interesting result. And also he generalizes it. So he basically says that a homomorphism counting problem can be solved in m to the power directory width of that particular pattern. So in particular, if the directory width is 1, then the homomorphism counting can be solved in linear time. In our paper, what we prove is that the directory width of 1 is exactly the subgraph for which the length of the induced cycle is at most 5. So we give a tighter characterization for this complicated concept of directory width to a much more simpler concept of length of the longest induced cycle. We show that if a graph has length of the longest induced cycle of at most 5, then its directory width is 1 and vice versa. So this was the main algorithmic result in our work. As a corollary, we get that for any graph which has longest induced cycle length of at most 5, the homomorphism counting problem is linear time solvable. Now, I have a few more technical slides that goes into the details of how we do it. But I'll actually skip that part. But if you're interested, I'm happy to talk about them offline. This part is basically shows how we exploit or how the length of the longest induced cycle is related to this concept of directory width. But yeah, these are some technical details. Very happy to talk about them offline if you're interested. So I'll just conclude here. So the first result that we had was for the subgraph count K problem. We are trying to count all K vertex subgraph. And we show that if K is at most 5, we can do it in linear time. If K is bigger than 6, then there is always some subgraph that we can't count in linear time. The next question that we asked, can we precisely characterize which subgraph we can count in linear time? So for this, first we consider the homomorphism counting problem. We show that there is a very easy and nice characterization. If the length of the longest induced cycle in your pattern is at most 5, you can count the homomorphism in linear time. And if not, cannot do it in linear time, of course, assuming the triangle counting conjecture. And we also show that this has some implication for the subgraph counting problem as well. It's not as clean as the homomorphism counting, but it says that for any subgraph, look at its quotient graphs. And if all the quotient graphs has longest induced cycle length to be at most 5, then you can count the subgraphs. You can get the subgraph count in linear time as well. But if some of them has length of the longest induced cycle more than 5 or more than 6, then you can't do it in linear time. Now I'll end with few open problems. So one theoretical question that comes out of this is characterizing for higher order runtimes. So for example, can we get a characterization for quadratic time algorithms as well? Now, what is the barrier for, what kind of subgraphs are the barrier for quadratic time algorithms? And we've observed that cycles are not the barrier. So no matter how large your cycle is, you can always count them in order m square time. So if you're trying to really look for quadratic time algorithms, you have to go beyond cycles, and probably it's going to be a more complicated structure. And another work, it's more algorithmic. For tree decompositions, we know many algorithms that actually gives a tree decomposition when the value of the tree width is small. So we ask, can such algorithm exist for directed or DAG tree decompositions as well? Can we find the DAG tree decompositions efficiently? And this might lead to more efficient algorithms for these problems in practice as well. So this is all I had to talk. I'll be very happy to take any questions, and thank you for listening to me.
All right, so thank you for very nice talk. Are there any questions for Suman?
I have a question. Do you have like an intuition of why like going from 5 to 6 makes the problem very hard? Like
yeah, we have a vague intuition. So let's say I'm looking at 6 cycles. So let's say, sorry, let me just. So let's say I'm trying to count 6 cycles. So the way to count this would be to first convert this into a acyclic orientation and then counting this acyclic orientation in this graph. So let's say I'm looking at an orientation that has components like this. This consists of 3 out-out wedges. So we observe that for all patterns which does not have a 6 cycle, or the length of the cycle is less than 6, we can always decompose into 2 such components, not 3. But as soon as we have a 6 cycle, we get these 3 out-out wedges. And now in the input graph, we are kind of trying to look for these out-out wedges and trying to see if they give me a 6 cycle or not. If this number was 2, then we can maintain some hash table and get these counts. But as soon as this number becomes more than 2, we have 3 components or higher, then it becomes then it becomes intractable to do it in linear time. But again, this is not a very precise intuition, but yeah.
Okay, thank you. Yeah, that's gets the idea.
To follow up on my colleague's question, you mentioned that independent sets are relevant to this work, and I believe 6 is also the magic number for the hardness of even approximately counting independent sets. So do you think there might be a connection there, or is it just 2 6s that are unrelated?
That's an interesting question. We have not actually thought about that, so I'm not sure. But that's yeah. I mean, we have not thought about it, but it's a very good question. Now that you mentioned, yeah, I think that's something worth looking into. But yeah, I don't have any intuition about that at this point.
Can you show the result of your ITCS result one more time?
Yeah.
Like the one that you use this DAG to count.
Yeah. Sorry, yeah, this one you mean?
Yeah. So why can't you like count other like larger subgraphs with the same technique?
No, you can count the larger subgraphs. The runtime will now might increase. So for example, let's say you are trying to count this 6 cycle, right? So 6 cycle, one particular pattern that you get is this collection of 3 such out wedges, right? There's 3 of them interacting at various points. So now what you have to do, the first step is to enumerate all such patterns. This you can do in linear time because there are m alpha such patterns. Now you have to check whether there exist 2 other patterns which intersect with it in the nice way in order to get the 6 cycles, right?
Oh, I see, I see.
So this you can't do it in linear time. So for each pattern, you have to basically check 2 other patterns whether they connect in the right way to form the 6 cycles. But if there was only one other pattern, then you can do some kind of hashing and you can try to get this count. But once you have more than two patterns, then it becomes intractable.
But sorry, if you are trying to count stars, let's say, stars of arbitrary size, then I guess the same technique would give you m to the power of alpha to the size of that star, right?
Yeah. You can count stars in linear time. Yeah.
Any other questions for Suman? Okay, so if there are no...
Is that because the independent sets involved in star graphs are very sparse and well-behaved?
Sorry, say that again, please.
Regarding Shahzad's question, stars are easy. Does that have something to do with the fact that independent sets in star graphs are very sparse and well-behaved?
I mean, so okay, stars are easy for another reason also. Like, so you can basically consider every age, like we are doing here. Now, star is basically how many out degree this vertex has, and then just taking all possible combinations of that. I mean, it's just a numeric number, right? So it's I mean, in fact, even in the original graph, if you're just trying to count the number of stars for every vertex, you can just take the degree choose 2, degree choose 3, and so on. And that will give you the number. So basically, you just need to enumerate, like go over all the vertices, look at its degree, do some computation, and you can get the star counts.
Right. I feel a little bit silly now. I guess I was thinking about why the lower bound didn't apply.
Yeah. Yeah, I mean, I don't immediately see any connection with the independence.
But similar to what you said about the clique, I believe.
So you mean like why the oh, I see. Okay. Yeah, right. So all the quotient graph for stars also will not have any large cycles, right? Yeah. Right.
So I have another question. Like this decomposition that you decompose a graph, like a subgraph to stars and cycles.
Okay.
If you want to use a similar technique for this, that would fail because of the cycles, right?
Sorry. So
let's say you want to count an arbitrary size subgraph, and you just decompose it to stars and cycles.
Right. Okay.
Then you try to count like this.
Right. If yeah, it depends on the length of the cycle that you have decomposed this into. Yeah. And if that cycle is larger, then yeah, you will probably have a problem. I mean, although I don't remember that decomposition statement precisely where you are decomposing this into a collection of cycles and stars, because it might still be possible that in that decomposition you come up with a large cycle, although the length of the induced cycle is not that large in that pattern. So in that case, you can still count it. But that decomposition, I think, was helpful in this other like approximate counting regime, where you are doing some kind of sampling to get these counts. So those might not be the perfect candidate for getting exact counts.
Yeah, Lorenzo has a question.
Hello, thank you very much for the talk first. So this is a question that's not included in your talk. So, so I guess my curiosity here is whether there are parallel algorithms with optimal speed up under these degeneracy assumptions, such as the one that you considered that you're aware of.
Yeah, I mean, I have seen some subgraph counting problem in the parallel regime where they use the degeneracy ordering. So the degeneracy ordering is kind of ubiquitous for various of this subgraph counting problem. But I'm not very familiar with what kind of techniques internally they use. So this overall idea, the one that I, yeah, this particular structure is used quite frequently, where you have the input graph, you do one set of pre-processing to get some kind of directed acyclic graph.
Right.
Many times you don't actually do the degeneracy ordering because it's a sequential process where you are removing minimum degree vertex in each iteration, but there are some parallel improvement possible over there if you're happy with some kind of approximation that still has this property that the out degree is not too large. So you can make it in like log n rounds of parallel computations, and you can get some ordering. And then you try to count in that directed graph. So I have seen some, I'm familiar with some MapReduce work, but not, I mean, yeah, I don't know the technical details of how people do this in the parallel community, but yeah, I have seen some work that uses this degeneracy ordering, the vertex ordering of the graph to speed up the computations. Yeah.
Yeah, I guess like the intuition would be that if a graph has low degeneracy, probably is pretty separable, so it's probably easy to partition it and assign to workers. Okay, thank you very much.
Yeah, thanks.
Okay, so if there are no more questions, let's thank Suman one more time.
Yeah, thank you for having me.
Thank you.
Thanks. Okay, thanks everybody.